This is the interior of the Menga dolmen in Andalusia. The central monolithic slab, capstone number 5, is estimated to weigh 150 tons. It was transported and positioned here between 3800 and 3600 BCE. Moving a mass of this scale creates a tension with the established timelines of the region. During this period, the archaeological record for Iberia contains no evidence of the centralized state apparatus or the large-scale social hierarchies usually associated with projects of this magnitude. To understand the physical reality of the site, we have to map the specific geometry of the structure. The upright pillars are set at precise dipping angles, creating a series of load paths designed to stabilize the 150-ton roof through compression. These engineering details suggest a level of technical expertise that may have existed independently of a centralized state. If the structural physics of Menga can be explained through localized mechanical knowledge, it would suggest a different model for Neolithic social organization. This search for structural patterns often encounters a geological counterpart. In the Pu Langka National Park of Thailand, the Pu Tok Noi sandstone appears to mimic the geometry of monumental masonry. While it resembles biological scales, the formation is the result of thermodynamic geomorphology. Over 100,000 years, intense thermal stress caused the rock's outer crust to expand and fracture into a predictable, interlocking polygonal pattern. We are executing a forensic audit of both sites, using precise spatial data, complex structural mechanics, and deep geomorphology to identify the actual processes that created these anomalies. Whether human-engineered or naturally formed, these structures are governed by measurable physical laws. By auditing the data, we can move past speculative narratives and establish a strictly empirical account of the landscape. The engineering of Menga reveals itself in the asymmetry of capstone C1. The stone's uneven thickness forces an unequal distribution of weight across its supporting pillars. To counteract this uneven load, the builders manipulated the depth of their trenches and the stratigraphic polarity of the upright elements. By aligning the natural bedding planes of the rock with the downward force, they ensured the stone would compress rather than shear, preventing a total system collapse. This control over spatial geometry is especially clear at the rear of the chamber. Backstone O12 interfaces directly with uprights O11 and O13 to form a precise 83-degree angle. Because placing these multi-ton stones vertically is highly unstable, the builders utilized a wooden wedge, driven over an external lateral ramp. This wedge inserted calculated horizontal pressure against the 83-degree upright setup. Inserting this wedge forcefully alters the balance point of the heavy upright. The resulting displacement allowed the builders to adjust the massive stone laterally, locking it tightly against blocks already placed on their sides. During the final placement phase, a dedicated counterweight system absorbed and redirected the kinetic energy, allowing the builders to lower the stone with absolute control. Menga is a highly coordinated exercise in gravitational leveraging. The builders substituted the need for tens of thousands of workers with a localized empirical mastery of mechanical advantage. This is a view of the Rano Raraku crater on Easter Island, the primary quarry for the monolithic Moai statues. For decades, the sheer volume of these figures scattered across the terrain was cited as proof of an imperial expansion. To test that assumption, researchers constructed a comprehensive structure-from-motion photogrammetry model of the crater, built from over 11,000 UAV images. Embedded within this high-resolution data are unfinished moai still attached to the bedrock by thin stone keels along their backs, documenting the exact extraction technique used by the carvers. The spatial map isolates 30 distinct independent quarrying foci. Natural topographical boundaries physically separate these clusters, preventing any single unified oversight of the production. The design of the statues themselves reinforces this independence. The moai were carved with an off-center gravity profile, shifting the mass heavily toward the base and the front. This enables a dynamic rotational pivoting motion. By manipulating the center of gravity to lower the friction coefficient, the builders minimize the lateral force required to move the statue. A very small team of workers could effectively walk a massive stone across the island. 30 distinct workshops operating simultaneously, paired with low-friction transport physics, demonstrates that moai production relied on horizontal, clan-based social networks. Complex cooperative behavior emerged without hierarchical control. The selection of materials for monumental construction was dictated by local geology. In Egypt, the Neo-Proterozoic Aswan granites, located within the Nubian Shield, served as the primary sourcing province for ancient monoliths. Geologists use Booger gravity anomaly mapping to identify deep subsurface structures. The highest gravity anomalies, measured between -13.5 and -22.0 milligals, map the precise locations of dense, unquarried crystalline horsts. These dense ridges stand in sharp contrast to deep sediment-filled grabens, which register much lower gravity anomalies ranging down to -48.3 milligals. The granite bedrock within these high-density zones contains specific structural constraints. The rock is naturally fractured by massive north-south and northeast-southwest joint sets. These primary joints interact directly with northwest-southeast Pan-African shear fabrics. Over millions of years, this deep-time tectonic grid naturally sliced the bedrock into pre-configured rectangular blocks. Ancient builders specifically targeted the grayish-black and coarse pink Monzo granites from this region because spectral imaging confirms these specific outcrops are structurally stable and free of deformational shear zones. The stonemasons did not carve large-scale shapes into a solid, unbroken mountain. They located and exploited these existing natural joint networks to extract intact obelisks and statues. Ancient structural sourcing was a highly targeted exploitation of deep basement tectonic faulting mapped onto the surface geology. We can apply the same rigorous geological analysis to the Phu Lanka National Park. Local beliefs often explain the Naka Cave sandstone formations through narratives of cursed kings or petrified prehistoric snakes. The physical reality involves a 100,000-year cycle of extreme diurnal thermal stress. The sandstone continuously expanded under intense daytime heat and then contracted rapidly in the cold night air. This relentless thermal stress forces a mechanical failure. The outer crust of the sandstone fractures along neat, interlocking geometric polygonal patterns. Once the rock mechanically fractures, the chemical weathering phase begins. Over millennia, rainwater infiltrates the geometric cracks. The water triggers a specific chemical reaction, dissolving the calcareous and siliceous cement that binds the individual sandstone grains together. This combination of chemical dissolution and mechanical polishing drives a process called spheroidal weathering. It aggressively rounds the sharp corners of the polygonal blocks, creating a smooth, overlapping texture. Subsurface two-dimensional electrical resistivity tomography confirms that these surface weathering patterns are directly dictated by the underlying Tachek strike-slip fault system. The serpent-like visual anomaly of Naka Cave is the strict product of deep-time thermal stress and chemical dissolution, governed entirely by the geometry of regional tectonic jointing. The forensic audit extends beyond the physical manipulation and weathering of stone. We must also account for the invisible physics contained within megalithic enclosures, the field of archaeoacoustics. This is the heavy, dry stone masonry forming the entrance to the subterranean rock-cut galleries of Chavin de Huántar in the Andes. These narrow, geometric chambers operate under highly specific spatial constraints. Acoustic testing inside these passages reveals a recurring pattern. The architecture forces resonance to lock precisely at 110 Hz. Inside these enclosures, short reverberation times and dense early reflections cause modal standing waves to compound rapidly against the tight geometric walls. Neurophysiological studies establish a direct biological response to these conditions. Study exposure to a 110 Hz acoustic tone directly alters human brainwave activity. These ancient sensory landscapes were engineered to induce neurological entrainment, establishing a precise psychoacoustic parameter directly into their structural monumentality. The gravitational load path leveraging of Menga, the tectonic fault line exploitation in Aswan, and the acoustic calibration at Chavin all point to a singular conclusion. Early human modification of the landscape represents a relentless, empirical integration of physics, thermodynamics, and neurobiology. Modern archaeological chronologies continuously fail to anticipate this level of decentralized technical mastery over physical laws. The raw material evidence strictly defies this.
It demands a different framework for how we analyze the engineering of the ancient world.